In this mini lecture, we're going to talk about elastic forces. And we'll see kind of this elastic idea come again when we talk about spring energy. When we apply a force to a material, it either stretches or compresses depending on the direction of force. There was a scientist whose last name was Hooke, and Hooke determined that the change in the length of an object and the force were directly proportional to each other. So that force is equal to some constant k times the change in the length of the object. So the force that you apply to change the length is equal to the change in the length of that object times this some constant k. But this happens with all materials to some degree. The units for, if we're talking about like stretching out a spring, the units for Hooke's spring constant K here are Newton over meter, or newtons per meter. Okay, so here we have, for example, 3 different materials that we're going to stretch. And here we have a thin nylon string, a thick nylon string, and then steel. And we are going to put some mass on it. This mass has some weight that is constant, and we're going to put that same mass on all 3 of these materials and see how much they stretch. So we're going to call L sub 0 the original length of this material. Okay, and that's what you see here in yellow. So when we put the mass on here, then our thin nylon string gets stretched by this distance that we're calling delta L. That's the change in length after you've put on that mass. And then over here, when we look at our thick nylon string, we see that when we put on that same mass, we do not stretch the material as much. And then whenever we do it to a steel piece of wire, we stretch it even less. Well, most materials have an elastic region over which you can stretch them or compress them and they won't break. Compressing or stretching materials within this elastic region allows them to still return to their original form after the force is removed. So like a rubber band, you can stretch it to some degree and it will still stretch back to its original shape and it's all okay. But every rubber band has a force that you can apply where if you exceed that, you break the bonds in the material and you can't assemble it back together again. So the elastic region is the region in which you can stretch a material or compress it and it will still be happy to come back to its original state. So in this graph here, we've got on the vertical axis how much you can stretch a material, and on the horizontal axis we've got the force that you're applying. So you see that there's this region that we call the linear region here. We've got a straight line. This is the region in which Hooke's law is obeyed, when the applied force is equal to our spring constant times the distance over which you stretch it. If you start applying too much force to these materials, then you can get outside of this region where Hooke's law applies, and eventually we'll reach a region where you apply just too much force and the material just cannot take it and it fractures or breaks. We change the length in a material when a force is applied to an object parallel to its length. And we either can stretch it, that's a tension force, or we can compress it by pushing down. There was a scientist with the last name of Young. Young had some ideas to sort of improve upon what Hooke came along with Hooke's law. Young's work modified Hooke's law by taking into account the length of the object. Or here we're thinking about the length of a spring or a rod. So Young determined this equation right here that says that the force applied over the cross-sectional area to which it is applied equals what we call the Young's modulus times an experimental constant times the distance that you stretch or compress that material divided by the material's original length. So this quantity here that we call the force over the area, later we'll see that this is a pressure, but right now we're calling this the stress on an object. The stress is equal to our Young's modulus times what we call the strain. The strain is the ratio of how much did you change the length of that object divided by the length of that object's original length. The spring constant K of the equation that we saw for Hooke's law, in terms of Young's law right here, is the following, that the spring constant K is equal to Young's modulus times the cross-sectional area over the length of the original object. We're going to use Young's equation here for compression in order to solve a real-world problem. How much does your leg shorten when you stand on it? We're going to calculate the change in length of the upper leg bone when you support weight on it. Before we do that, I want to show you the stress strain curve for a typical mammalian tendon. So here we've got what we call we've got the force on the horizontal axis, the force applied, and then we've got the amount that that material is stretched, that the tendon is stretched. And this would be the force applied to the tendon. There's a region that you call the toe region, where the fibers start to align in the direction of stress. So you're applying a little bit of force, a little bit of tension, and over this region right here in the toe region, the fibers within the tendon start to align within that direction of the applied tension. And then we have the linear region. That's our linear region for Hooke's law, over which the fibers are now aligned with the fibers of the tendon are aligned with the direction of that tension force, and then the fibers start to stretch out along that same direction. And then eventually we know that whenever you apply too much force to a tendon, it will eventually break. And when you reach the failure region for that tendon, that's the region where you've applied too much force, you've stretched that tendon out too much, and then the fibers in the tendon start to break and fall apart, and you can't put them back together again.
We are going to calculate how much your leg shortens when you stand on it. Our bones are compressible, and we're going to calculate that right here. So calculate the length, the change in length of the upper leg bone, our femur, when a 70-kilogram man supports 62 kilograms of his mass on that one leg. We're going to assume the bone to be equivalent to a uniform rod that is 40 centimeters long and that has a radius of 2 centimeters. So this rod is basically a cylinder. Okay. And then we're told the compression value for Young's modulus for the bone, and that's 9 times 10 to the 9 Newton over meter squared. Big number. And remember that the Young's modulus is essentially a measurement of the elasticity of a material. So we've got all of these knowns here. We want to find this quantity that I'm calling delta L here. That's how much we end up compressing our bone, or that's the change in length of our upper leg bone here. So here's our original leg bone, 40 centimeters long, a radius of 2 centimeters, and then even though it tells us the total mass of the man is only supporting 42 kilograms, or sorry, 62 kilograms, and so this is the mass that we're going to care about. Okay, so that man applies a mass of 62 kilograms onto that leg, and in doing so compresses that leg a distance that we're going to call delta L, the change in the length of the leg. So we're compressing it actually in this situation. So we're going to try to figure out what is this compression. And to do that, we're going to use the equation for stress on a compressed object. We saw it earlier when I was going through the slides. And so that equation is the force applied to the material divided by its cross-sectional area here, cross-sectional area to which that force is applied. This whole term, the force over the area, we're calling stress. And that equals our Young's modulus, this coefficient, times the change in length over the original length. Okay, we are trying to solve this equation for delta L. So I have to multiply both sides by the length, original length. When I do that, this cancels here and here. So then I've got this equal to our Young's modulus, delta L, equals the force over the area times the original length. And then we have to divide both sides by the Young's modulus. Okay. So then we find that the change in length is going to equal the original length divided by our Young's modulus times the applied force over the cross-sectional area to which that force is applied. Okay, so the original length of our bone was 40 centimeters. We are going to need to write that in meters, so 0.4 meters divided by our Young's modulus, 9 times 10 to the 9 Newton over meter squared. And then we need to multiply it by the force applied. The force applied is going to be that mass times gravity. We're applying 62 kilograms times gravity. 62 kilograms times 9.8 meters per second squared. Sometimes I say gravity. What I really mean is the acceleration due to gravity, 9.8 meters per second squared, divided by the cross-sectional area of this bone. We're told the radius of that bone, which we're approximating as a long cylinder or rod. We're told the radius. So the cross-sectional area of a circle, or the area of a circle, is pi times the radius squared. Okay, this equation is also on the very back of your equation sheet, last page of your equation sheet. So the area here is going to be pi times the radius, 0.02 meters squared. I gave it to you in centimeters, but we've got here kilograms, we've got meters over second squared. We want this, we've got our Young's modulus and Newton meters, Newton over meter squared. So we want to put all those distances in meters, okay? And so now we just compute this, plug and chug, and we find that the distance that that leg gets compressed is 2.15 times 10 to the minus 5 meters. Okay, so we are compressing our bones just a little bit every time we put any weight on them.
There are two other equations that are kind of similar to what we just used. One uses something called the shear modulus, and the other uses something called the bulk modulus, but the ideas are the same. So a shear we're going to think about as a sideways stress. A shearing force arises from a sideways stress. The deformation of the object is perpendicular to its length. So here, let's say, a bookshelf. We've got the length of the bookshelf right here. We're applying a force on top of the bookshelf perpendicular to this length. And then this deformation that we're causing on this material is this distance delta x here. So we start when the bookshelf is upright before I apply any force, and then that horizontal distance over which I can push it, that's the delta x in this experiment here. And then A is this cross-sectional area here that is parallel to the direction in which I'm applying the force. Here's our equation for shear deformation. Delta x is that distance perpendicular to the length over which I'm applying that force, equals 1 over what we call the shear modulus, determined experimentally, times the force applied, divided by the area of this material that's parallel to the force, and then multiplied by the length of the body. And then this length is the length that's perpendicular to the applied force. So I could give you a problem where I ask you to calculate the shear deformation of a bookshelf, for example, like this, and you would use this equation right here. Then we have the bulk modulus, changes in volume. The bulk modulus characterizes the response of a substance to uniform squeezing. And a really great example would be if you take a material and you submerge it and it falls all the way down to the bottom of the ocean. It's experiencing some squeezing pressure from the fluid of the ocean surrounding it. And that would be a problem that you could do using our relationship that takes into account the bulk modulus. So this changing in volume arises in particular, yes, when an object is submerged in a fluid, like I was just describing. The relationship of a volume stress to the volume strain, so the volume stress would be this F over A. The volume strain would be our change in volume over the original volume, is given like this. So we've got the change in volume over the original volume equals 1 over the bulk modulus, again, of experimental property of the material, times the force applied uniformly inward on all surfaces of the material, divided by the surface area of the material. Now, I'm not going to solve problems using our relationship between volume stress and volume strain and shear stress and shear strain with you. But it's a similar idea to what we do when we solve the problem that was talking about the elastic strain. And so I'm going to maybe ask you to solve a few problems like this on your own in the homework.